On the launch pad, 5 engines are about to do something that sounds almost impossible. Burn through 15 tons of fuel every second and somehow not tear themselves apart. Each one produces over 1.5 million pounds of thrust. Multiply that by 5, and you have enough force to lift a 6.5 million pound rocket off the ground, against the full pull of Earth's gravity. But thrust like that doesn't come from a bigger engine or more fuel. It comes from a series of extraordinarily precise engineering decisions about pressure, temperature, and the shape of a single piece of metal. This is how rocket engines turn a controlled explosion into millions of pounds of thrust. Rocket thrust is a direct application of Newton's third law of motion. For every action, there is an equal and opposite reaction. Gases are expelled downwards. Unlike air-breathing jet engines, rockets carry their own oxidizer. This vital onboard supply allows them to generate thrust and operate effectively even in the vacuum of space. Rocket engines combine a fuel and an oxidizer. When ignited, these propellants undergo a rapid chemical reaction, releasing vast amounts of energy to create hot gas. This potent mixture ignites within the combustion chamber. Here, immense pressures, ranging from 150 to 4,350 psi, are generated, creating superheated gas. The controlled explosion of propellants within the chamber produces a huge volume of gas. This gas is incredibly hot, often thousands of degrees Fahrenheit, and under immense pressure. The design of the engine nozzle is critical. It doesn't just vent exhaust, it's precisely shaped to accelerate these hot gases to extremely high velocities. The narrowest point of the nozzle is called the throat. Here, the gas flow is choked, meaning it reaches Mach 1.0, establishing the engine's mass flow rate. Beyond the throat, the nozzle flares outward. This expansion allows the high-pressure gas to expand further, converting its thermal energy into kinetic energy. This acceleration process is key. The nozzle design meticulously converts pressure and temperature into immense speed, propelling the exhaust gases out at thousands of miles per hour. Thrust is determined by the mass flow rate of the exhaust and its exit velocity. Minimally, thrust equals mass flow rate times exit velocity, F_cum. The generalized thrust equation also includes the effect of exit pressure against ambient pressure, plus AE open parenthesis, P minus P0 close parentheses. This factor further contributes to the total generated thrust. Liquid rocket engines use propellants stored separately as liquids. Pumps then feed these into the combustion chamber, offering control over thrust and shutdown capability. Solid rocket motors use a pre-mixed solid propellant grain. Once ignited, they burn continuously until all propellant is consumed, providing immense sustained power. Hybrid rockets combine elements of both, typically using a solid fuel with a liquid or gaseous oxidizer. This offers advantages like safety and throttle ability. Monopropellant rockets use a single substance decomposed by a catalyst. Though simpler, they typically produce less thrust and are used for smaller maneuvers. The Saturn V's first stage used 5 F1 engines, each capable of generating approximately 1.5 million pounds of thrust. These engines were titans of rocketry. With 5 F1 engines firing simultaneously, the Saturn V's first stage produced the colossal 7.5 million pounds of thrust needed for liftoff. Liquid oxygen and kerosene were pumped at incredible rates into the F1's combustion chamber, mixing under extreme pressure to generate the stupendous thrust. The F1's thrust chamber, where fuel and oxidizer mixed and burned, was the heart of this massive engine, producing the intense heat and pressure for thrust. Liquid oxygen was precisely injected into the F1's combustion chamber through a domed manifold. This ensured efficient mixing with fuel for maximum energy release. The F1's thrust was transmitted through a gimbal bearing. This allowed the engine's direction to be slightly adjusted, providing crucial steering control during ascent. Witnessing an F1 engine is awe-inspiring. Its immense size and the raw power it generated underscore the engineering marvel required to launch spacecraft. Rocket engine efficiency isn't just about raw thrust. Specific impulse, is a key metric, measuring how much thrust is generated per unit of propellant consumed over time. While higher thrust means faster acceleration, a high specific impulse means the engine uses propellant more economically, crucial for longer missions and interplanetary travel. The entire process relies on controlled high-speed ejection of mass. By expelling gas forcefully through the nozzle, the rocket generates immense forward thrust. It's a brilliant transformation. Chemical energy from propellants is converted into the thermal and kinetic energy of exhaust gases, creating the force needed to overcome gravity. This self-contained system makes rockets uniquely suited for space. They can generate thrust without external air, pushing tirelessly through the vacuum of the cosmos. From immense multi-million-pound thrust engines like the F-1 to smaller thrusters enabling precise maneuvers, rocket propulsion is a testament to human ingenuity and physics. By mastering the physics of expelling mass at high speeds, engineers unlock the extraordinary power needed to explore our solar system and beyond. The science behind rocket thrust is fascinating. If you found this explanation helpful, please like, share, and subscribe for more deep dives into aerospace.